You probably know that the Earth's surface is made up of different pieces called tectonic plates, which move around and interact with each other. This movement causes earthquakes, volcanoes, mountains, and other geological features. But did you know that this was not always the case? In fact, for most of Earth's history, the surface was more or less stuck together in a single piece without any plate boundaries or large-scale horizontal motions. This is called the stagnant-lid model, and it lasted from the formation of the Earth about 4.5 billion years ago until about 3 billion years ago. But how do we know this? And what implications did it have on life as we know it? Well, today we're going to talk about a fascinating topic: how the Earth's tectonic regime changed over time and what it means for life on Earth. So sit back and relax, because this episode is going to be interesting. I'm your host, MrEarthGuy, and you're listening to Earth SciShow. One of the ways we can study the history of the Earth's tectonics is by looking at rocks that contain magnetic minerals, such as magnetite. When these rocks form, they record the direction and intensity of the magnetic field at the time. By dating these rocks and measuring their magnetization, we can reconstruct how the magnetic field has changed over millions or billions of years. The magnetic field is generated by the movement of molten iron in the outer core, which acts like a giant dynamo. The magnetic field protects us from harmful cosmic rays and solar wind, and also helps us navigate using compasses. But the magnetic field is not constant or stable. It varies in strength and direction, and sometimes it even flips completely, reversing the north and south poles. One of the most amazing discoveries from these studies is that the Earth's magnetic field has reversed polarity many times in the past. The most recent reversal happened about 780,000 years ago, and the average time between reversals is about 200,000 to 300,000 years. That means we are overdue another reversal, but we don't know exactly when or how fast it will happen. But what happens during a reversal? Well, it's not like a switch that flips instantly. It's more like a gradual process that can take thousands of years. During this time, the magnetic field becomes weaker and more complex, with multiple poles appearing and disappearing around the globe. This would create problems for navigation, communications, and satellite systems that rely on these magnetic fields. It could also expose us to more radiation from space, which could have effects on our health and climate. But don't panic just yet. There's no evidence that a magnetic reversal causes mass extinctions or major catastrophes. Life on Earth has survived many reversals before and will likely adapt to the future ones as well. In fact, some scientists think that reversals may even stimulate evolution by creating new challenges and opportunities for living organisms. So why does the magnetic field reverse in the first place? Well, that's still a mystery that scientists are trying to solve. One theory is that it has to do with the chaotic nature of fluid motions in the outer core, which are influenced by factors such as temperature, pressure, rotation, and gravity. Sometimes these motions become unstable and disrupt the normal pattern of the dynamo, leading to a reversal. Another theory is that it has to do with interactions between the inner core and the outer core. The inner core is solid iron, and it also rotates slightly faster than the rest of the planet. This creates a torque on the outer core, which may affect the dynamo as well. Sometimes these interactions may trigger a reversal or prevent one from happening. And there are many other factors that may also influence the magnetic field, such as changes in the mantle, crust, or even external sources like the sun or other planets. The magnetic field is a complex system that depends on many variables, and we still have a lot to learn about how it works and how it affects us. But what does this have to do with tectonics? Well, as it turns out, there is a connection between magnetic fields and the movement of plates. The magnetic field can tell us whether or not there were plates moving around in different directions at different times in Earth's history. How? Well, remember when we said that rocks record the direction and intensity of magnetic fields when they form? If those rocks are part of a plate that moves around over time, they will record different directions and intensities depending on where they are located on Earth. For example, if a rock forms near the equator where the magnetic field is weaker and horizontal, it will record a low intensity and east-west direction. But if that rock moves to a higher latitude and where the magnetic field is stronger and vertical, it will record a higher intensity and a north-south direction. By comparing these records from different rocks of different ages from different places on Earth, we can reconstruct how the plates have moved over time. This is called paleomagnetism, and it's a powerful tool for studying the history of tectonics. One of the most amazing discoveries from paleomagnetism is that the continents were not always in their current positions. In fact, they have moved around a lot over time, sometimes forming major supercontinents and sometimes breaking apart. The most recent supercontinent was Pangaea, and it existed about 300 million years ago. Since then, Pangaea has split into the continents we know today, and they are still moving around at a rate of a few centimeters per year. But what about before Pangaea? What about the ancient rocks that are older than 3 billion years? What do they tell us about the tectonics of early Earth? Well, this is where things get really interesting. In a brand new study published by a team of international scientists, they've revealed some surprising findings about the tectonic regime of early Earth. The authors used zircon crystals from South Africa and Australia that contain magnetic information to reconstruct the history of Earth's magnetic field and its relation to the movements of the continents. And for those that might be unaware, zircon is a mineral that forms in igneous rocks such as granite or basalt. It's very resistant to weathering and erosion, and it can survive billions of years. Zircon also contains traces of uranium and lead, which can be used to date the age of the crystal. In addition to this, zircon also contains tiny inclusions of magnetite. This is a magnetic mineral that records the direction and intensity of the magnetic field when the zircon forms. And by dating these zircons and measuring their magnetization, the authors were able to reconstruct how the magnetic field has changed over time from 4.2 billion years ago to 3.3 billion years ago. This is an incredible achievement because these are some of the oldest rocks on Earth, and they are very rare and difficult to find and study. So what did they find? Well, they found that the magnetic field was very different in early Earth than it is today. For one thing, it was much weaker, only about 10 or 20% of its current strength. This means that the dynamo in the outer core was less efficient, most likely because the inner core had not formed yet. But more importantly, they found that the magnetic field was very stable and constant in both direction and intensity for long periods of time, up to hundreds of millions of years in fact. This means that there was no evidence of magnetic reversals or variations in the field that would indicate plate motions or changes in latitude. This is very different from what we see today, where the magnetic field changes frequently and reverses every 300,000 years. This suggests that the tectonic regime of early Earth was also very different from what we see today. Instead of having plates moving around and colliding with each other, creating mountains and volcanoes and earthquakes, the early Earth had a stagnant lid, where the surface was more or less stuck together in one single piece, without any plate boundaries or large-scale horizontal motions. The evidence suggests that the stagnant lid model lasted from the formation of the Earth about 4.5 billion years ago until about 3 billion years ago. During this time, the Earth was cooling down from its initial molten state and gradually forming a solid crust over its mantle. The crust was probably thicker and stronger than today's crust, making it harder to break into plates. The heat from the core and mantle was escaping through plumes or heat pipes that created volcanic hotspots on the surface. One example of a hotspot today are the Hawaiian Islands. The stagnant lid model had some advantages and disadvantages for life on Earth. On one hand, it provided a stable environment without major catastrophes or changes in climate caused by plate motions or polar wander. On the other hand, it limited the geochemical cycling of elements between the crust and mantle, which is important for maintaining habitable conditions on Earth. The authors suggest that life on Earth originated and evolved during this stagnant lid mode, without requiring plate tectonics as we know it today. This is remarkable because it shows that life can adapt to different tectonic regimes on different planets. And you may be asking the question, if the Earth was once one large plate, how did plate tectonics start on Earth? And why did it start when it did? Well, these are still open questions that scientists are trying to answer. One possibility is that plate tectonics started as a result of changes in the mantle temperature or composition over time, which made the crust thinner and weaker and more prone to breaking into plates. Another possibility is that plate tectonics started as a result of impacts from large asteroids or comets, which created cracks or scars on the surface that acted as precursors for plate boundaries. Whatever the cause, plate tectonics started sometime after 3 billion years ago, and has been operating ever since. Plate tectonics has transformed the surface of our planet, creating new continents and oceans, mountains and valleys, volcanoes and earthquakes, and plate tectonics has also influenced the evolution of life on Earth by creating new habitats and niches, new challenges and opportunities, new sources of energy and nutrients, and new ways of exchanging genes and information. Plate tectonics is a unique feature of our planet, and we don't know if it exists on any other planet in the universe. Some scientists think that plate tectonics is essential for life because it regulates the climate and the chemistry of the atmosphere and oceans. Others think that plate tectonics is not necessary for life because life can adapt to different environments and conditions. What do you think? Do you think that plate tectonics is a blessing or a curse for life on Earth? Do you think plate tectonics is common or rare in the universe? And do you think that plate tectonics will continue or stop in the future? Do let me know your thoughts and opinions in the comment section below. And that's all for today's episode of Earth SciShow. I hope you enjoyed learning about the history of the Earth's tectonics and its relation to the magnetic field. If you enjoyed this content, please consider subscribing or following on your podcast platform. And I look forward to sharing more in the next episode. You've been listening to Earth SciShow, and I am your host, MrEarthGuy. And remember, stay curious.